And now in this lecture I will answer two questions. In the first question we find out the area of this green shape that is inside square TSQP. And in the second question we find out the area of this green shape that is inside square ABCD. So we start with the first question. In the drawing we have two squares. This is the big square TSQP and this is the small square ABCP. In addition, we have quadrilateral MBCP is equal to 27 square units in its size, and this is triangle AMP is equal to 9 square units in its size. Again, our task is to find out the area of this green shape. First of all, it is easy to see from the drawing that the area of the small square ABCP is equal to the area of this quadrilateral MBCP, that is equal to 27 square units in its size, plus the area of this triangle AMP. So in total, the area of this quadrilateral ABCP will be equal to 27 plus 9, that is 36 square units in its size. So I write it down. The area of square ABCP is equal to 36 square units in its size. Repeat again, the area of this small square ABCP is equal to 36 square units in its size from one side, but from the other side, we know that the area of any square equals to the length of one side squared. So the area of this square ABCP will be equal to the length of side AP squared. That is to say, it is equal to AP squared. So repeat again. On one side, the area of the small square ABCP equals to 36 square units in its size, but from the other side, the area of square ABCP equals to the length of one side of square ABCP squared. That is to say, it is AP squared. So in this equation, AP squared equals to the square root of the area of the small square ABCP equals to 36. We will derive that AP squared equals to 36 here we'll take a root out of this equation and we get that AP equals to the square root of 36, that is 6. AP equals to 6 units in its length. This is side AP of the small square ABCP, that equals to 6 units in its length. So we know that the area of this triangle AMP is equal to 9 square units in its size. So write it down. The area of triangle AMP is equal to 9 square units in its size according to what is given in the question. This is from one side, but from the other side, we know that the area of any triangle equals to the base of the triangle times the height over 2. Therefore, the area of this triangle AMP will be equal to the base AM times the height AP over 2. So if we derive from one side, the area of triangle AMP equals to 9 square units in its size, but from the other side, the area of triangle AMP equals to the base AM times the height AP over 2. From this equation, we derive that AM times AP over 2 equals to 9. We already found out that AP equals to 6 units in its length. So we substitute AP in this equation by 6 and get that AM times 6 over 2 equals to 9. 6 over 2 is 3, so in total, this is the equation we have 3 times AM. 3 times AM equals to 9. Here we divide this equation by 3 and get that AM equals to 9 over 3, that is 3. AM equals to 3 units in its length. This is the missing side AM, that equals to 3 units in its length. We know that all the angles inside any square are right angles, so the small square ABCP, this is the right angle. Therefore, triangle AMP is a right triangle, so I'll copy triangle AMP in an equation. We'll implement the Pythagoras theorem on this right triangle, triangle AMP. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the progression of Pythagoras theorem. Okay, this is triangle AMP, that is the proof from the original drawing. This triangle AMP according to the Pythagoras theorem, MP square, that is the square of the hypotenuse, equals to AM square plus AP square. So write it down. MP square, that is the square of the hypotenuse, equals to AM square plus AP square. MP is the missing side, so leave it as it is. So it is MP square equals to AM square. AM is 3, therefore AM square is 3 square, that is 9. Plus AP square. AP is 6, therefore AP square is 6 square, that is 36. So in total MP square equals to 9 plus 36, that is 45. MP square equals to 45. Here we substitute 45 by 9 times 5 and get that MP square equals to 9 times 5. Here we take out of this equation and finally we get that MP equals to the square root of 9, that is 3. Inside the root we left only with 5. So total MP equals to 3 times square root of 5 units in its length. This is side MP is equal to 3 times square root of 5 units in its length. In the next step, we find out the length of this missing 9 segment MB. We know that all the sides in any square are equal to each other. So in the small square ABCP, AP equals to 6, and therefore AB also must be equal to 6. MB equals to AB minus AM. So write it down. MB equals to AB minus AM. So MB equals to AB is 6, minus AM is 3, so in total MB equals to 6 minus 3, that is 3. MB equals to 3 units in its length. We know that all the angles inside the square are right angles. So in the big square TSQP, this is a right angle. And those two angles are defined as vertex angles, and you know that vertex angles are equal to each other. So if we find the size of this angle as alpha, then the size of this angle must be also equal to alpha, because they are equal to each other. In the big right triangle AMP, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus alpha. Y equals 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, in the small right triangle TMB, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be also equal to 90 degrees minus alpha, according to the same rule that states that the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see from the drawing that those two right triangles are similar to each other according to angle similarity rule. That is to say, those two angles are both equal to alpha, and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So if you prove that all the angles in the big right triangle AMP are correspondingly equal to all the three angles of this small right triangle TMB, and therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. Actually prove that those two triangles are similar to each other according to angle similarity rule. So the big right triangle AMP is similar. This is the sign of similar to the small right triangle TMB according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We derive that side AP of the big right triangle AMP over side TB of the small right triangle TMB is equal to side AM of the big right triangle AMP over side TM of the small right triangle TMB, and it is also equal to side MP of the big right triangle AMP over side MB of the small right triangle TMB. And again, from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We will derive that side AP of the big right triangle AMP over side TB of the small right triangle TMB is equal to side AM of the big right triangle AMP over side TM of the small right triangle TMB, and it is also equal to side MP of the big right triangle AMP over side MB of the small right triangle TMB. AP equals to 6 over TB. TB is the missing side, so we need to see this. And it is equal to AM. AM is 3 over TM. TM is the missing side, so leave it as it is. And is equal to MP. MP is 3 times square root of 5 over MB. MB equals to 3 units in its length. So in total, we should find out that 6 over TB equals to 3 over TM equals to 3 times square root of 5 over 3. We have 3 in the numerator and 3 in the denominator, so 3 will get cancelled, and we left only with square root of 5. So as we know, we should find out that 6 over TB equals to the square root of 5, and it is also equal to 3 over TM. Those two sides are equal to each other, so we get the first expression from those two sides. That is to say, 6 over TB equals to the square root of 5. Here we will multiply this equation by TB, then we will divide it by square root of 5, and we get that TB equals to 6 over square root of 5 units in its length. This is side TB, that is equals to 6 over square root of 5 units in its length. Those two expressions are equal to each other, that is to say, square root of 5 equals to 3 over Tm. So I have known square root of 5 equals to 3 over Tm. Here we will multiply this equation by Tm and then we divide it by square root of 5, and we get that Tm equals to 3 over square root of 5 units in its length. This is side TM. Is equals to 3 over square root of 5 units in its length. In the next step, we find out the length of side TP of the big square TSQP. From the drawing it is very easy to see that TP in total equals to TM plus MP. So, write it down. TP equals to TM plus MP. TP equals to TM plus MP. So TP equals to TM. TM equals to 3 over square root of 5 plus TM. TM equals to 3 times square root of 5. So in total, TP equals to 3 over square root of 5 plus 3 times square root of 5. So TP equals to 3 over square root of 5. Here we multiply this number 3 times square root of 5 by square root of 5, and then we divide it by square root of 5 in order to come out of this number. And we get that square root of 5 times square root of 5 is 5, and 5 times 3 is 15. So in total, in the numerator of this expression we have 15, and we have to divide it by square root of 5. So in total, TP equals to 3 plus 15, that is 18, over square root of 5 units in its length. TP equals to 18 over square root of 5 units in its length. So this is side TP, that is equals to 18 over square root of 5 units in its length. So as you know, TP equals to 18 over square root of 5 units in its length. Our task is to find out the area of this green shape. So what is the area of the green shape? From drawing, it is very easy to see that the area of this green shape in total equals to the area of the big square TSQP minus the area of this quadrangle MBCP minus the area of this small right triangle TMB. So write it down. The area of this green shape, that is the area that we are looking for this question, it is equal to the area of the big square TSQP minus the area of this quadrangle MBCP, that is equal to 27 square inches inside according to what is given in the question. Minus the area of this right triangle TMB. The area of the big square TSQP equals to the length of one side squared. That is to say, it is the length of side TP squared, or it is TP squared. And again, the area of the big square TSQP equals to TP squared minus the area of this quadrangle MBCP is equal to 27 square units inside according to what is given in the question. Minus 27 minus the area of this small right triangle TMB. The area of this small right triangle TMB equals to the base of the right triangle TMB, that is TB, times the height, that is TM over 2. So the area of the small right triangle TMB equals to the base TB times the height TM over 2. So again, the area of the small right triangle TMB equals to the base TB times the height TM over 2. TP equals to 18 over square root of 5 units is 9. Therefore, TP squared equals to 18 over square root of 5 squared minus the area of quadrangle MBCP is equals to 27 square units in size minus the area of the small right triangle TMB is equals to TB, the base TB. The base TB equals to 6 over square root of 5 units in its length times the height TM, that is equals to 3 over square root of 5 units in its length divided by 2. So in total, if you know that the area of the small right triangle TMB equals to the base, that is 6 over square root of 5 times the height, that is 3 over square root of 5 divided by 2. The area of the big square TSQP equals to 18 over square root of 5 units in its size. So 18 over square root of 5 units squared is 18 squared, that is 324 over square root of 5 squared, that is 5. So in total, the area of the big square TSQP equals to 324 over 5 square units in its size minus the area of quadrangle MBCP, that is 27, minus the area of the small right triangle TMB. So this is question. So in the numerator we have 6 times 3, that is 18, that is minus 18. In the numerator we have square root of 5 times square root of 5 is 5, and 5 times 2 is 10. So in total, the area of the small right triangle TMB equals to 18 over 10 square units in its size. 324 over 5 is 64.8 minus 27 minus 18 over 10 is minus 1.8. So now if you want to know that the area of the green shape is equal to 64.8 minus 27 minus 1.8. 64.8 minus 1.8 is 63, and 63 minus 27 is equal to 36 square units in its size. Again, if you follow that the area of this green shape, that is the area that we are looking for in this question, is equal to 36 square units in its size. So we finished with the first question. In the next step, I will present you the second question. We will solve the second question of this lecture. Our task in the second question is to find out the area of this green shape. So in the drawing we have square ABCD. We know that one side of square ABCD equals to 10 units in its length. Therefore AB equals to BC equals to CD equals to AD equals to 10. In addition, inside this square ABCD we have this quarter circle. We know that the center of this quarter circle is here at point A. So point A is the center of the quarter circle, point B is the point of the quarter circle itself, therefore AB is the radius of the quarter circle, that is equals to 10 units in its length. AO is also the radius of the quarter circle, that is equals to 10. AO is also one side of square BCD, that is equals to 10 units. In addition, we have this semicircle. We define the radius of this semicircle here at this point as point O. We know that the diameter BC of the semicircle equals to 10, and therefore the radius must be equal to 10 over 2, that is 5. So the radius BO is 5 for the semicircle, and the radius OC of the semicircle is also equal to 5 units in its length. In the next step, we define the intersection point between this quarter circle and this semicircle. This point is point M. And we join points O and M together by a straight line. Point O is the center of the semicircle, point M is the point of the semicircle itself, therefore OM is the radius of the semicircle, is equal to 5. In the next step, we join points A and M together by a straight line. Point A is the center of the quarter circle, point M is the point on the quarter circle itself, therefore AM is the radius of the quarter circle, this is equal to 10. AM is a tangent to this semicircle at point M. So AM is a tangent. So here we can implement rule 1. According to rule 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. The radius OM of the semicircle, that is equals to 5. The radius OM is drawn to point M, that is the point of tendency of tangent AM with this semicircle. And whenever your radius is drawn to the point of tendency, then tangent AM will be perpendicular to the radius MO. If AM is perpendicular to MO, it means that this angle equals to 90 degrees according to rule 1. We know that all the angles inside the square are right angles. So the big square BCD, this is the right angle. In the next step, we will join points A and O together by a straight line. By joining points A and O, we create another two right angles. This is the right angle ABO, and this is the right angle AOM. So in the next step, we prove that those two right angles can point to each other according to side rule. So all those two right angles can point to each other. First of all, side OP of the right triangle ABO equals to side OM of the right triangle AOM. They are both the radii of the semicircle that is equals to 5 and therefore they are equal to each other. OP equals to OM equals to 5. OP equals to OM equals to 5. In addition, side AB of the right triangle ABO is equal to side AM of this right triangle AOM. They are both the radii of the concentric circle that is equals to 10 and therefore they are equal to each other. AB equals to AM equals to 10. Again, AB equals to AM equals to 10. And finally, AO is a common side that belongs to both triangles, so AO equals to itself is a common side that belongs to both triangles. So if you hold on that, again, AO equals to itself, it's a common side that belongs to both triangles. So if you hold on that all the three sides of this right triangle ABO correspond equal to all the three sides of this right triangle AOM, and therefore those two right triangles can go into each other according to angle similarity rule. So I write it down. If you hold on that the right triangle ABO congruent, this is the sign of congruent, to the right triangle AOM, according to angle similarity rule. And from the fact that those two right triangles can go into each other, we will derive that those two angles must be also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, and therefore those two corresponding angles must be also equal to each other. So, if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to the rule that I mentioned. Likewise, from the fact that those two right triangles can go into each other, we will derive that those two angles must be also equal to each other according to the same rule that corresponding angles in congruent triangles are equal to each other. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta because they are equal to each other according to the rule that I mentioned. In the next step, we will implement the Pythagoras theorem on this right triangle ABO. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So I'll copy this right triangle ABO in a new page and we implement on it the Pythagoras theorem. Here by PT זה בראשון פרופדור הסטרואיד. This is right ABO, that the form of the drawing, this is right ABO. AO squared, that is the square of the hypotenuse, equals to AB squared plus BO squared. So write it down. AO squared, this is the square of the hypotenuse, equals to AB squared plus BC squared. AO is the missing side, so it is AO squared equals to AB squared. AB is 10, therefore AB squared is 10 squared, it is 100, plus BO squared. BO is 5, therefore BO squared is 5 squared, it is 25. So in total, AO squared equals to 100 plus 25, this is 125. AO squared equals to 125. Here we substitute AO squared by 25 times 5 and get that AO squared equals to 25 times 5. Here we take a look out of this equation. And finally we get that AO equals to the square root of 35 is 5, so inside the root we left only with 5. So AO equals to 5 times square root of 5 units inside. This is inside AO. This is equals to 5 times square root of 5 units inside. We know that we continue to focus on the right triangle ABO. We know that the sum of the angles in any triangle is equal to 180 degrees, and therefore the sum of the angles in the right triangle ABO must be equal to 180 degrees. So which angles we have in the right triangle ABO? We have alpha plus beta plus 90 degrees. In total, it must be equal to 180 degrees. So as you know that the right triangle ABO, alpha plus beta plus 90 degrees, in total must be equal to 180 degrees. Here we subtract 90 degrees from the equation. We get it alpha plus beta equals to 180 degrees minus 90 degrees is 90 degrees. So alpha plus beta equals to 90 degrees. Here we subtract alpha from this equation, and finally we get that beta equals to 90 degrees minus alpha. So our task, actually, before we continue, we find out the size of angle alpha and angle beta. And we will continue to focus on the right side ABO. So we copy again the right side ABO. New page. especially. This is the right triangle ABO that are coming from the original drawing. This right triangle ABO, sinus alpha equals to BO over AO. Again, sinus alpha equals to BO over AO. So, I don't know. Sinus alpha equals to BO over AO. So sinus alpha equals to BO, that is 5 over AO. We only found out that AO equals to 5 times square root of 5. AO equals to 5 times square root of 5. So in total we found out that sinus alpha equals to 5 over 5 times square root of 5. Again, sinus alpha equals to 5 over 5 times square root of 5. We have 5 in the numerator, 5 in the denominator, so 5 get cancelled. And we left only with 1 over square root of 5. So in total, we should found out that sinus alpha equals to 1 over square root of 5 units in its length. We would like to find out the size of angle alpha itself, or the value of angle alpha itself. In order to find out the value of angle alpha, we operate the opposite function of sine on the result of sine alpha, that is 1 over square root of 5. In this way, we get the size of angle alpha itself. That is to say, we operate the opposite function of sine, that is arc sine, on the result of sine alpha, that is 1 over square root of 5, and will be equal to the size of angle alpha. Arc sine of 1 over square root of 5 is 26.565 degrees. So it is equal to alpha. So if you found out that angle alpha equals to 26.565 degrees in its size. This is angle alpha that is equal to 26.565 degrees in its size. Here we multiply alpha by 2 and we get that 2 alpha equals to 2 times 26.565 degrees. It actually equals to 53.13 degrees in its size. So actually, the big angle the big angle BAM. This is the big angle BAM. Again, this is the big angle BAM. This is equals to alpha plus alpha is 2 alpha, and we just find out that 2 alpha equals to 53.13 degrees in its size. So now 2 alpha equals to 53.13 degrees in its size. We already found out that beta equals to 90 degrees minus alpha. Beta equals to 90 degrees minus alpha. So beta equals to 90 degrees minus alpha, and alpha equals to 26.565 degrees in its size. So it is minus 26.565 degrees. So So beta equals to 90 degrees minus 26.565 degrees. This is equal to 63.435 degrees. So if you found out that angle beta equals to 63.345 degrees in its size. And therefore 2 beta is equal to 2 times 63.435, that's actually equals to 126.87 degrees in its size. Angle MOB, this is angle MOB. This is equal to beta plus beta, that is 2 beta, is equal to 126.87 degrees in its size. Our task is to find out the area of this green shape. So first of all, we join points M and B together by a straight line. By joining points M and B, we divided this green shape into 2 parts. This is the first part and this is the second part. The first part is a segment. So we define the upper segment as segment MUB. And again, upper segment is defined as segment we define the upper segment as segment MUB. This is segment MUB. The second part is the lower segment. This is the lower segment. So we define the lower segment, this segment as segment MLB. So again, this is the lower segment that is defined as segment MLB. It is very clear from the drawing that the area of the upper segment MUB plus the area of the lower segment MLB, in total it is equal to the area of the green shape. So we find out the area of the lower segment MLB, and then we find out the area of the upper segment MUB. We add the 2 areas together, and this will be the area of this green shape, that is the area that we are looking for this question. So first of all, we find out the area of this lower segment MLB. So I copy sector ABM in a new page and we analyze this sector AMB. So what is a sector? A sector is a portion of a circle enclosed by 2 radii and the arc between them. So I copy the sector and then I explain in detail. It is exactly a sector. Actually, this is sector ABM, this is coming from the original drawing. a sector is a portion of a circle, you can see that the green shape A or B is a sector and is a portion of this circle enclosed by two radii and the arc AB between them. The two radii are defined as the legs of the sector, so the angle between the legs of the sector is theta. So repeat again, a sector is a portion of a circle enclosed by two radii and the arc AB between them. So what is it? Is like a slice of a pizza. So what is the area of this sector A or B? The area of this sector A or B equals to pi r squared. That is the area of the circle that contains the sector times the angle between the legs of the sector, that is theta, over 360 degrees. Repeat again. The area of the sector A or B equals to pi r squared. That is the area of the circle that contains the sector times the angle between the legs of the sector, that is theta, over 360 degrees. So we use the new formula in order to find out the area of this sector, sector ABM. According to the formula that I presented to you, the area of sector ABM will be equal to pi r squared, that is the area of the circle that contains this sector, times the angle between the legs of the sector, that is 53.13 degrees, over 360 degrees. The two legs of the sector, each of them is equal to 10. They are both the radii of the quarter circle. AB equals to AM. They are both the radii of this quarter circle. The radius of the quarter circle equals to 10. So R equals to 10. Therefore R squared is 10 squared, that is 100, so pi r squared is 100 pi times 53.13 degrees over 360 degrees. The value of this expression, that is to say 100 pi times 53.13 degrees over 360 degrees, in total it is equal to 46.3646 square in size. And again, if you found out that the area of this sector ABM, in total it is equal to 46.3646 square in size. Our task is to find out the area of the lower segment BLM. This is the lower segment BLM that we have to find out the area of it. Again, this is the lower segment BLM. We have to find out the area of this lower segment. From the drawing, it is the same lower segment here, BLM, that the COVID. So from the drawing, it is very easy to see that if you remove from this sector ABM, this triangle ABM, we get exactly this segment BLM. Again, if you remove from this sector ABM this triangle ABM, we get exactly this segment BLM. And the first segment BLM will be equal to the area of sector ABM This is sector ABM. We have already found out that the area of this sector ABM equals to 46.3646 coordinates in size. From this sector, we have to subtract this triangle ABM. So minus the area of triangle ABM. This is triangle ABM. This angle equals to 53.13 degrees in its size. AB equals to 10, AM also equals to 10. So what is the area of this triangle ABM? In order to find out the area of this triangle, I'll present to you in a formula that will help us to find out the area of any triangle. This is triangle ABC that could be any triangle. In this triangle ABC, side AB equals to A units in its length, side AC equals to B units in its length, and the angle between side AB and side AC is theta. So the area of this triangle ABC that could be any triangle equals to A times B, that is the multiplication of two sides by each other, times sinus the angle that is between those two sides, that is theta, over 2. But again, the area of this triangle ABC that would be any triangle equals to A times B times sinus theta over 2. So we use the new formula in order to find out the area of this triangle ABM. According to the new formula that I presented you, the area of this triangle ABM will be equal to AB times AM, that is the multiplication of two sides by each other, times sinus the angle between those two sides, that is sinus 53.13 degrees, divided by 2. So if we again to the area of this triangle ABM equals to AB times AM times sinus 53.13 degrees over 2. AB is 10 times AM is also 10 times sinus 53.13 degrees, this is 0.8 divided by 2. 10 times 10 is 100, 100 over 2 is 50, and 50 times 0.8 is 40. So today we found out that the area of this triangle ABM is equal to 40 square units in its size. And therefore, the area of the lower segment B and M will be equal to the area of sector ABM, that is 46.3646, minus the area of this triangle ABM, that is equals to 40 square units in its size. 46.3646 minus 40 equals to 6.3646 square units in its size. So in total, we found out that the area of this segment B and M is equal to 6.3646 square units in its size. Okay. This is the lower segment B and M. We just found out that the area of the lower segment B and M equals to 6.3646 square units in its size. In the next step, we'll find out the area of the upper segment BUM. This is the upper segment BUM. In order to find out the area of this upper segment BUM, I'll copy sector OBM in a new page and we'll analyze this sector OBM. This is sector OBM. That's the comment on the drawing. The rounded sign above OBM is a sign for a sector. It means sector OBM. The angle between the legs of the sector is the angle BOM. That is equals to 2 beta. We already found out that 2 beta equals to 126.87 degrees in this side. OB equals to OM. They are both the radii of the semicircle. That is equals to 5. OB equals to 5. OM also equals to 5. So what is the area of this sector? Sector OBM. According to the formula that I presented to you a couple of minutes ago, the area of this sector OBM will be equal to pi r squared. That is the area of the circle that contains this sector times the angle between the legs of the sector, that is 126.87 degrees over 360 degrees. So in total, we found out that the area of this sector OBM equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the circle, that is 126.87 degrees over 360 degrees. R is 5, therefore r squared is 5 squared, that is 25. So pi r squared is 25 pi times again 126.87 degrees over 360 degrees. The value of this expression in total, that is to say the value of this expression, that is 25 pi times 126.87 degrees over 360 degrees. In total, it is equal to 27.678 square units in its size. So I should know that the area of this sector OBM is equal to 27.678 square units in its size. Our task is to find out the area of this upper segment BUM. This is the upper segment BUM that we have to find out the area of it. The green shape, it is segment BUM. We have to find out the area of this segment BUM. So I copy the segment here. This is segment BUM. This is segment, the upper segment BUM. We have to find out the area of this upper segment BUM. So what is the area of the upper segment BUM? From the drawing, it's very easy to see that if you remove triangle BMO from sector BUM, we get exactly segment, the upper segment BUM. Again, if you remove from this sector BUM the area of triangle BUM, we get exactly this segment BUM. Therefore, the area of segment BUM will be equal to the area of sector BOM This is sector BOM. area of triangle BOM. This is triangle BOM. The angle between side BO and side OM is 126.87 degrees in its size. BO equals to OM equals to 5. And then again, if you remove from this sector BOM this triangle BOM, you get exactly segment BUM. Therefore, the area of segment BUM equals to the area of sector BUM minus this triangle BOM. We already found out that the area of this sector BOM is equal to 27.678 square inches in size minus the area of triangle BOM. According to the formula that I presented to you, the area of this triangle BOM will be equal to BO times OM, that is the multiplication of two sides by each other, times sinus the angle between those two sides, that is actually sinus 126.87 degrees over 2. And again, in total, the area of this triangle BOM is equal to BO times OM, that is the multiplication of two sides by each other, times sinus the angle between those two sides, that is again 126.87 degrees over 2. BO is 5, OM is also 5, so 5 times 5 is 25, times sinus 126.87 degrees. Sinus 126.87 degrees is equal to 0.8, so this 25 times 0.8 divided by 2. 25 over 2 is 12.5, and 12.5 times 0.8 is 10. So total, if you want to know that the area of this triangle BOM is equal to 10 square inches in its size. And the area of this the upper segment BOM will be equal to the area of sector OBM, that is 27.678, minus the area of this triangle BOM, that is 10 square inches in its size. So 27.678 minus 10 is equal to 17.678 square inches in size. So the area of this upper segment BOM equals to 17.678 square inches in size. This is the upper segment BOM. We just now found out that the area of this upper segment BOM equals to 17.678 square inches in size. Our task is to find out the area of this green shape. And we already found out that the area of the upper segment BUM is equal to 17.678 square inches in size, and the area of this lower segment BLM is equal to 6.3646 square inches in size. And therefore, the area in total of the green shape will be equal to the area of the upper segment BUM, that is 17.678, minus the area of the lower segment BLM, that is equal to 6.3646 square inches in size. So I did not found out that the area of the green shape in total this is the green shape that according from the original domain. So the area of this green shape will be equal to the area of the upper segment BUM, that is equal to 17.678 square inches in size, plus the area of the lower segment BLM, that is equal to 6.3646 square inches in size. So in total, the area of this green shape will be equal to the area of the upper segment BLM plus the area of the lower segment BLM. That is actually 17.678 plus 6.3646. Write it down. The area of the green shape in total equals to the area of the upper segment BUM, that is 17.678 square inches in size, plus the area of this lower segment BLM, that is equals to 6.3646 square inches in size. And 17.678 plus 6.3646, in total it is equal to 24.0426 square inches in its size. And again, if you found out that the area that we are looking for in this question, that is the area of this green shape, in total it is equal to 24.0426 square inches in size. So we finish with the second question. In the next step of the lecture, we'll start with the first question, of course. In the first question, our task is to find out the area of this green shape. So in the drawing we have two squares. This is the big square TSQP and this is the small square ABCP. In addition, we have this quadrilateral MBCP. This is equal to 27 square units inside. We have also this triangle AMP. That is equal to 9 square units inside. Again, our task is to find out the area of this green shape. So first of all, it is very easy to see that the area of this square ABCP it is equal to the area of quadrilateral MBCP. This it is equal to 27 square inches in size, plus the area of this triangle AMP that is equal to 9 square inches in size. So in total, the area of this square ABCP equals to 27 plus 9, that is 36 square inches in size. So from one side, we found out that the area of this small square BCP is equal to 36 square inches in size. But from the other side, we know that the area of any square equals to the length of one side squared. Therefore, it will be the length of side AP squared or AP squared. So from the other side, the area of the small square BCP equals to AP squared. And from this equation, AP squared equals to the area of square BCP equals to 36. We derive that AP squared equals to 36. Here we took out of this equation and we found out that AP equals to the square root of 36. This is side AP, is equals to 6 units in its length. We know that all the angles inside the square are right angles. So in the small square BCP, this angle is a right angle. And therefore triangle AMP is a right angle. Triangle AMP is a right angle. So in the right triangle AMP, we know that the area of this right triangle AMP equals to 9 square inches in size from one side, but from the other side, the area of this triangle AMP also equals to the base of the triangle times the height over 2. the base is AM, the height is AP over 2. So in total, the area of this triangle AMP will be equal to the base AM times the height AP over 2. Again, from one side, the area of the right triangle AMP is equal to 9 square units in its size, but from the other side, the area of triangle AMP equals to the area of any triangle that is equal to the base of the triangle times the height over 2. The base is AM, the height is AP over 2. So in total, we found out that AM times AP over 2 equals to the area of the right triangle MP equals to 9. From this equation, we will derive that AM times AP over 2 equals to 9. AP is 6, so we substitute AP by 6, and we found out that AM times 6 over 2 equals to 9. 6 over 2 is 3, so in total, we found out that 3 times AM equals to 9. Here, we divide this equation by 3, and finally get that AM, we divide this equation by 3, and finally found out that AM, the missing side AM equals to 9 over 3, that is 3. This is the missing side AM, that is equal to 3 units in its length. In the next step, I copied the right triangle AMP in a new page, and we implemented the Pythagoras theorem of this right triangle AMP. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. This is the right triangle AMP, that is according to the original drawing. This right triangle AMP, MP squared, that is the square of the hypotenuse, equals to AM squared plus AP squared. MP is the missing side, so we will see this. So we have MP squared, that is equals to AM squared. AM is 3, therefore AM squared is 3 squared, that is 9, plus AP squared. AP is 6, therefore AP squared is 6 squared, that is 36. So in total, MP squared equals to 9 plus 36, that is 45. So MP squared equals to 45. MP squared equals to 45. Here we substituted 45 by 9 times 5, and therefore we got that MP squared equals to 9 times 5. Here we took a root out of this equation, and finally found out that MP equals to the square root of 9, that is 3. So inside the root we left only with 5. So in total we found out that MP equals to 3 times square root of 5 units in its length. This is side MP. This is equal to 3 times square root of 5 units in its length. What is the length of this line segment MB? MB equals to AB minus AM. And again, MB equals to AB minus AM. We know that all the sides of square ABCP are equal to each other. AP is 6, therefore AB is also 6. So MB equals to AB, that is 6, minus AM, that is 3. So in total, MB equals to 6 minus 3, that is 3. So this is the line segment MB, that is equal to 3 units in its length. We also know that all the angles inside the square are right angles. So in the big square TSQP, this is the right angle. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha, because they are equal to each other. So in the big right triangle AMP, this angle equals to alpha, this angle equals to 9 degrees, and therefore this missing angle must be equal to 9 degrees minus alpha. Y equals 9 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees, that is the sum of the angles in a triangle. Likewise, in the small right triangle AMB, this angle equals to alpha, this angle equals to 9 degrees, and therefore this missing angle must be equal to 9 degrees minus alpha, according to the sum rule that says that the sum of the angles in a triangle is equal to 180 degrees. So in the next step, we prove that those two right triangles are similar to each other according to angle similarity rule. So why those two right triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So if you found out that all the three angles of this big right triangle AMP corresponding equal to all those three angles in this right triangle TMB, and therefore those two right triangles are similar to each other according to angle, similar return. And again, if we found out that the big right triangle AMP is similar, this is the sign of similar to the small right triangle TMB according to angle, similar return. And for the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AP of the big right triangle AMP over side TB of the small right triangle TMB is equal to side AM of the big right triangle AMP over side TM of the small right triangle TMB, and it is also equal to side MP of the big right triangle AMP over side MB of the small right triangle TMB. And again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We derive that side AP of the big right triangle AMP or side TB of the small right triangle TMB is equal to side AM of the big right triangle AMP or side TM of the small right triangle TMB, and it is also equal to side MP of the big right triangle AMP or side MB of the small right triangle TMB. AP 6 over TB. TB is the missing side, so it is, and it is equal to AM. AM is 3 over TM. TM is the missing side, so it is this, and it is also equal to MP. MP is 3 times square root of 5 over MB. MB is 3. So in total, I found out that 6 over TB equals to 3 over TM equals to 3 times square root of 5 over 3. We have 3 in the numerator, 3 in the denominator, so 3 we get cancelled, and we left only with square root of 5. So in total, we have found out that 6 over TB equals to square root of 5 equals to 3 over TM. Those two sides are equal to each other, so we can do the first equation from those two sides. That is to say, 6 over TB equals to the square root of 5. Here we multiply this equation by TB, and then we divide it by square root of 5, and finally found out that TB equals to 6 over square root of 5 units in its time. This is side TB is equal to 6 over square root of 5 units in its time. Those two sides also equal to each other, so we can do this kind of equation from those two sides. That is to say, square root of 5 equals to 3 over TM. Here we have square root of 5 equals to 3 over TM. Here we multiplied this equation by TM, and then we divided by square root of 5, and finally found out that TM equals to 3 over square root of 5 units in its time. This is side TM, this is equals to 3 over square root of 5 units in its time. In the next step, we calculated the length of side TP of the big square TSQP. TP in total equals to TM plus MP. And again, TP equals to TM plus MP. So TP equals to TM, that is 3 over square root of 5, plus MP, that is 3 times square root of 5. And again, TP equals to TM, that is 3 over square root of 5, plus MP, that is 3 times square root of 5. So TP equals to 3 over square root of 5, and we multiplied this number 3 times square root of 5 by square root of 5, and then we divided by square root of 5 in order to become comfortable with this number. So square root of 5 times square root of 5 is 5, and 5 times 3 is 15. So in total, the numerator of this expression we have 15, and we have to divide it by square root of 5. So in total, actually found out that TP equals to 3 plus 15 over square root of 5. 3 plus 15 is 18 over square root of 5. So in total, we found out that TP equals to 18 over square root of 5 units in its time. This is side TP is equals to 18 over square root of 5 units in its time. Our task is to find out the area of this green shape. From the drawing, it is very easy to see that the area of this green shape in total is equal to the area of the big square TSQP minus the area of this quadrangle MBCP minus the area of this small right triangle TMB. Repeat again, the area of the green shape in total equals to the area of the big square TSQP minus the area of quadrangle MBCP minus the area of the small right triangle TMB. What is the area of the big square TSQP? The area of any square equals to the length of one square, the length of one side square. So the area of this square TSQP will be equal to the length of side TP squared. This is to say it is TP squared. So the area of the big square TSQP equals to TP squared. It is given as a question that the area of this quadrilateral MBCP equals to 27, so it is minus 27 and minus the area of the smaller triangle TMB. This is the area of the area of this smaller triangle TMB. The area of this smaller triangle TMB will be equal to the base TB times the ITM over 2. Again, the area of the smaller triangle TMB equals to the base TB times the ITM over 2. TB is equal to 5, TB equals to 6 over square root of 5, and TM equals to 3 over square root of 5. Again, TB equals to 6 over square root of 5, and TM equals to 3 over square root of 5 divided by 2. So, TP equals to 18 over square root of 5, therefore TP squared is 18 over square root of 5 squared, minus the area of quadrilateral MBCP is 27, and minus the area of the right small triangle TMB is equals to 6 times 3 over square root of 5 times square root of 5 times 2. 18 over square root of 5 squared equals to 18 squared, that is 324, over square root of 5 squared, that is 5. So in total, the big square SQP equals to 324 over 5 squared in size, minus the area of quadrilateral MBCB, that is 27, minus the area of the small rectangle TMP, that is equals to 6 plus 6 times 3 is 18, over square root of 5 times square root of 5 is 5, and 5 times 2 is 10. So in total, the area of the small rectangle TMB is equal to 18 over 10 square roots in size. So it is minus 18 over 10. 324 over 5 is 64.8, minus 27, and minus 18 over 2 is minus 1.8. 64.8 minus 1.8 is 63 minus 27. 63 minus 27 is 36. So total remember that the area of this green shape, this is the area that we are looking for in this question, is equal to 36 square units in size. So we finish with the first question. The next step I presented you with the second question, and we solve the second question of this lecture. In the second question, our task is to find out the area of this green shape. So in the drawing, we have square ABCD. We know that one side of square ABCD equals to 10 units in its length. Inside this square ABCD, we have the big quarter circle. Point A is the center of the quarter circle. Point B is the point of the quarter circle itself. Therefore, B is the radius of the quarter circle, that is 10. Likewise, AD is also the radius of the quarter circle, that is equal to 10 units in its length. In addition, inside this square ABCD, we have this semicircle. We define the center of this semicircle, this point is point O. BC is the diameter of the semicircle, that is 10, and therefore the radius must be equal to 10 over 2, that is 5. So the radius of B is 5, and the radius OC of the semicircle is also equal to 5 units in its length. In the next step, we define the intersection point between this quarter circle and this semicircle. This point is point M. And the joint points O and B together, O and M together by straight line. Point O is the center of the semicircle, point M is the point of the semicircle itself, therefore OM is the radius of the semicircle, that is equal to 5. Likewise, we join points A and M together by straight line. Point A is the center of the quarter circle, point M is the point of the quarter circle itself, therefore AM is the radius of the quarter circle, that is equal to 10. AM is actually a tangent to the semicircle at point M. So here we can implement rule 1 because we have the radius OM is equals to 5, the radius of the semicircle is equals to 5, the radius OM is drawn to point M, that is the point of tendency of tangent AM with this semicircle. And whenever your radius is drawn to the point of tendency, then tangent AM will be perpendicular to the radius MO. If AM is perpendicular to MO, it means that this AM equals to 90 degrees according to rule 1. We also know that all the angles inside the square are right angles. So the big square ABCD, this is a right angle. The next step, we join points A and O together, that's right angle. By joining points A and O, get those two right angles. This is the right angle ABO, and this is the right angle AOM. So the next step, we prove that those two right triangles can go into each other according to side rule. So when those two right triangles can go into each other, first of all, side OB of the right triangle ABO is equal to side OM of the right triangle AOM. They're both the radius of the semicircle is equal to 5, and therefore they're equal to each other. And again, OB equals to OM equals to 5. In addition, side AB of the right triangle ABO is equal to side AM of the right triangle AOM. They're both the radius of the closed circle that is equal to 10, and therefore they're equal to each other. And again, AB equals to AM equals to 10. And finally, side AO is a common side that belongs to both triangles, so we can write down that AO equals to itself is a common side that belongs to both triangles. So we can again know that AO equals to itself is a common side that belongs to both triangles. So if you found out that all the three sides of this right triangle ABO are corresponding equal to all those three sides of the right triangle AOM, and therefore those two right triangles can go into each other according to side rule. And again, if you found out that the triangle ABO congruent, this is the sign of congruent, to the right triangle AOM according to side rule. And from the fact that those two right triangles can go into each other, we know that those two angles must be also equal to each other according to the rule that corresponding angles can congruent triangles are equal to each other. Those two triangles can go into each other, and therefore those two corresponding angles must be also equal to each other in their sizes. So if you define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to the rule dimension. Likewise, from the fact that those two right triangles can go into each other, we will derive that those two angles must be also equal to each other according to the same rule that corresponding angles can congruent triangles are equal to each other. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta because they are equal to each other according to the rule dimensions. In the next step, I copied right triangle ABO in a new page and we implemented the Pythagoras theorem in this right triangle ABO. This is the right triangle ABO that is coming from the original drawing. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendicular. So the right triangle ABO, AO squared, that is the square of the hypotenuse, equals to AB squared plus BO squared. So AO is the missing side, so AO is the missing side, so leave it as it is, and it is equal to AB squared. AB is 10, therefore B squared is 10 squared, that is 100, plus BO squared. BO is 5, therefore BO squared is 5 squared, that is 25. So in total, AO squared equals to 100 plus 25, that is 125. AO squared equals to 125. Here we substitute 125 by 25 times 5, and we got that AO squared equals to 25 times 5. Here we took out of this equation and we found out that AO equals to the square root of 25 is 5, so inside the root we left only 5. So in total we found out that AO equals to 5 times square root of 5 units in its length. This is side AO that equals to 5 times square root of 5 units in its length. We continue to focus on the right triangle ABO. This is the right triangle ABO. In the right triangle ABO, the sum of the angles must be equal to 180 degrees according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So which angles we have in the right triangle ABO? We have alpha plus beta plus 90 degrees, in total it must be equal to 180 degrees. Repeat again, the right triangle ABO, alpha plus beta plus 90 degrees, in total it must be equal to 180 degrees. Here we subtracted 90 degrees from this equation, and we found out that alpha plus beta equals to 180 degrees minus 90 degrees is 90 degrees. Here we subtracted alpha from this equation, and finally found out that beta equals to 90 degrees minus alpha. We continue to focus on this right triangle ABO. So for triangle ABO in the new page, this is triangle ABO that is coming from the original drawing. In triangle ABO, sinus alpha equals to BO over AO. Sinus alpha equals to BO over AO. BO is 5. AO is 5 times square root of 5, so in total sinus alpha equals to 5 over 5 times square root of 5. We have sinus alpha equals to 5 over 5 times square root of 5. We have 5 in the numerator, 5 in the denominator, so 5 will get cut, and we left only with 1 over square root of 5. So sinus alpha equals to 1 over square root of 5. sinus alpha equals to 1 over square root of 5. Our task is to find out the value of angle alpha itself. In order to find out the value of angle alpha, we'll operate the opposite function of sine, that is arc sine, on the result of sinus alpha, that is 1 over square root of 5. In this way, we get the value of alpha itself. The value of angle alpha itself. The size of angle alpha or value of angle alpha. So the opposite function of sine is arc sine. We operated it on the result of sine alpha, that is 1 over square root of 5, and this will be equal to alpha. Arc sine 1 over square root of 5 is 26.565 degrees in its size. So in total, we should find out that alpha equals to 26.565 degrees in its size. Therefore, 2 alpha equals to 2 times 26.565 degrees, that is 53.13 degrees in its size. So this is again MAB, this is equals to 2 alpha, and 2 alpha equals to 53.13 degrees in its size. We already found out that beta equals to 90 degrees 1 alpha. Here, beta equals to 90 degrees 1 alpha. So beta equals to 90 degrees and 1 alpha, and alpha equals to 26.565 degrees. So 90 degrees minus 26.565 degrees is equal to 63.435 degrees. So in total, we found out that beta equals to 63.34 degrees in its size, and therefore 2 beta equals to 2 times 63.435 degrees, that is actually 126.87 degrees in its size. Actually, this is angle MOB, this is equals to 2 beta, angle MOB, and 2 beta equals to 126.87 degrees in its size. So angle MOB, in total, it is equal to 126.87 degrees in its size. Our task is to find out the area of this green shape. In order to find out the area of the green shape, we join points M and B together by straight line. By joining points M and B, we divided this green shape into 2 parts. We have the upper part, this is the upper part, and this is the lower part. The upper part is actually a segment. So we define this segment, the upper segment, as segment MUB. And the lower part is the lower segment. So define this lower segment as segment MLB. It is very clear that the area of the green shape in total will be equal to the area of the upper segment MUB plus the area of the lower segment MLB. So first of all, we found out the area of this lower segment MLB. So copy sector A and B in a new page. We analyze this sector in order to find out the area of the lower segment MLB. This is sector ABM, according from the original drawing. This sector. So what is a sector? A sector is a portion of a circle enclosed by 2 radii and the arc between them. And again, this is sector AOB. It is a portion of this circle enclosed by 2 radii and arc AB between them. The 2 radii are defined as the legs of the sector. Angle theta is the angle between those 2 legs of the sector. And the area of this sector in total equals to pi r squared, this is the area of the circle that contains the sector, times the angle between the legs of the sector, that is theta, over 360 degrees. So a sector is a portion of a circle enclosed by 2 radii and the arc between them, and the area of any sector equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is theta, over 360 degrees. Use this new formula in order to find out the area of this sector ABM. According to the formula that I represented you, the area of this sector ABM will be equal to the area of the circle that contains the sector, that is actually pi r squared, times the angle between the legs of the sector, that is 53.13 degrees, over 360 degrees. R is the radius of the quarter circle, that is 10. And therefore r squared is 10 squared, that is 100. So pi r squared is 100 pi times 53.13 degrees over 360 degrees. So in total, the value of this expression, 100 pi times 53.13 over 360 degrees, is equal to 46.4 46.3646 square units inside. So in total, if you found out that the area of this sector ABM equals to 46.3646 square units in size. Our task is to find out the area of this lower segment BLM. So I with this lower segment BLM. This is the lower segment BLM, and we have to find out the area of it. The area of this lower segment BLM will be equal to the area of sector ABM minus the area of triangle ABM. It's very easy to see from the drawing that if you remove from this sector ABM this triangle ABM, we get exactly segment BLM. Therefore, the area of segment BLM equals to the area of the sector ABM minus the area of triangle ABM. We already found out that the area of sector ABM equals to 46.3646 square units in size minus the area of triangle ABM. In order to find out the area of triangle ABM, I presented to you a new formula that will help us to find out the area of any triangle. Actually, this is triangle ABC that could be any triangle. Side AB equals to A units in its left, side AC equals to B units in its left, and the angle between side AB and side AC is theta. So the area of this triangle ABC that could be any triangle equals to A times B times sinus theta over 2. But again, the area of this triangle ABC equals to A times B times sinus theta over 2. So it is the multiplication of the two sides by each other times the angle between those two sides, that is theta over 2. We use the new formula in order to find out the area of this side ABM. According to the formula, the area of triangle ABM will be equal to AB times AM, that is the multiplication of two sides by each other, times sinus the angle between those two sides, that is 53.13 degrees over 2. So if again, the area of this side ABM in total equals to AB times AM times sinus 53.13 degrees over 2. AB is 10, AM is 10, so AB times AM is 10 times 10. Sinus 53.13 degrees is 0.8 divided by 2. 10 times 10 is 100, 100 over 2 is 50, and 50 times 0.8 is 40. So in total, if you found out that the area of this triangle ABM equals to 40 square units in its size. And therefore, in total, the area of this segment BLM will be equal to the area of sector ABM, that is 46.3646, minus the area of triangle ABM, that is 46.3646 minus 40 equals to 6.3646 square units in size. So she found out that the area of this lower segment BLM equals to 6.3646 square units in size. The next step, our task is to find out the area of this upper segment BOM. In order to find out the area of this upper segment BOM, I copy sector BOM in a new page and analyze this sector BOM. So here, this is sector BOM that I copied from the original drawing. The two legs of the sector, each of them equals to 5, and the angle between those two legs is 126.87 degrees. So according to the formula that I presented to you, the area of this sector MOB will equal to pi r squared, that is the area of the sector that contains the sector, times the angle between the legs of the sector, that is 126.87 degrees over 360 degrees. R is 5, therefore r squared is 5 squared, that is 25, so pi r squared is 25 pi, times 126.87 degrees over 360 degrees. So in total, the value of this expression, 25 pi times 126.87 over 360 degrees, in total it is equal to 27.678 square units in size. So if you found out that the area of this sector BOM is equal to 27.678 square units in size. Our task is to find out the area of this upper segment BOM. What is the area of the upper segment BOM? The area is equal to the area of sector BOM minus the area of triangle BOM. It is very easy to see from the drawing that if you remove from this sector BOM this triangle BOM, we get exactly segment BOM. Therefore, the area of segment BOM equals to the area of sector BOM minus the area of triangle BOM. We already found out that the area of this sector BOM equals to 27.678 square units in size, minus the area of triangle BOM. According to the formula that I presented to you, the area of this triangle BOM equals to BO times OM times sinus 126.87 degrees over 2. BO is 5, OM is 5, so BO times OM is 5 times 5, this is 25. Sinus 126.87 degrees is 0.8. divided by 2. So in total, the area of this triangle BOM equals to 25 times 25 over 2 is 12.5, and 12.5 times 0.8 is 10. So in total, we should know that the area of this triangle BOM equals to 10 square units in size. And therefore, the area of this upper segment BOM will be equal to the area of sector BOM, that is 27.678, minus the area of this triangle BOM, that is 10. So in total, 27.678 minus 10 is 17.678 square units in size. So we should find out that the area of this upper segment BOM equals to 17.678 square units in size. And therefore, the area of the green shape will be equal to the area of the upper segment BOM, that is 17.678, plus the area of the lower segment MLB, that is 673646 square units in size. This is the green shape that are coming from the original drawing. The area of this green shape equals to the area of the upper segment BOM, that is equal to 17.678 square units in size, plus the area of the lower segment BLM, that is equal to 6.3646 square units in size. So in total, the area of the green shape equals to 17.678 plus 6.3646. In total, it is equal to 24.0426 square units in size. But again, if you found out that the area that we're looking for in this question, that is the area of the green shape, in total it is equal to 24.0426 square units in size. Okay, thank you very much.